All right. Hello and welcome to the first Bi-State Math Colloquium of, what is this, fall of 2022. My name is Jacob Heidenreich, and I am the moderator and organizer of this, and I will be giving the first talk. My first talk here is, or the first talk on the Loras end of things, I should say. Last week, Platteville, the other state in the Bi-State Colloquium, had their first talk. So my talk today is called What We Can Learn About Things by Pouring Syrup on. Now, what are we getting at here? So I'd like to start asking you to think about this. What is math about? Now, math gives a lot of tools. We have a lot of equations we can use in physics and finance and all of that. But math as a science, what does it study in particular? What's its object? Like biology studies living things, physics studies forces of nature. What's the object of math aside from producing all of these tools for other fields?
Like connections and relationships between things.
Connections and relationships between things, right. So that's having a student of mine in the audience, that's a problem. They know the right answers sometimes. So in particular, it's looking at patterns in life, and math has been called sometimes the science of patterns. So one of the things we're going to do, one of the main goals of today's talk is to see a surprising pattern in life that we can prove mathematically. We're not going to prove it in this class. It's a little beyond the scope of this talk, but just to show an example of math as a science of patterns, what's a surprising pattern we might see. So the first thing we're going to do, oh, I didn't think this through. Hold on a second. All right. Here, actually, let me start. Take that. Haley, here, take this. Let's start with that. All right, hold on. So the first thing I have here is we have a whole bunch of shapes. These are dice for Dungeons and Dragons games. Where's my camera? Oh, so here's one die. Here's another one. Still projecting up there? Yeah. Okay, here's another one. So we have a bunch of shapes like this. And what I'm going to ask our audience to do, Kaylee, Derek, pick out one or two you like a lot, is to take the dice and count the number of faces, the number of corners that are called vertices, and the number of edges. And I am going to call up an Excel sheet here, share, and we're going to put on this what we find. So Kaylee, did you count your die already? How many faces does it have?
6.
6. How many edges does it have?
8.
Try again.
12.
There you go.
There's a few corners.
Corners. And how many corners does it have? That's 8. Okay. Derek, have you got some of them?
Yeah, I got a pyramid looking one.
Oh, you got a pyramid looking one. It is called a tetrahedron, tetra for 4. How many faces does it have?
4.
4. There you go. Very good. Edges.
I believe 6.
Yep, that's right. And corners, vertices.
4.
All right. So we have now exhausted all of our labor pool here in person for the talk. So we're going to have to do some double duty. Let's see, Kaylee, why don't you do, you do this one.
Okay. Yeah.
Okay. And Kaylee, why don't you do this one as well? And I'll do the tough one. I will do the one with 20 faces, 12 vertices. And let's see if I could figure out what the answer is supposed to be so I don't actually have to count them. Some might call that cheating. Actually, 30 edges. So here, let me stop the screen share and show you what I have. So that's this one right here, this fancy blue one right here. 12 faces, 30 edges, no, 20 faces, 30 edges, and 12 corners. All right, Kaylee, you got some results for us?
Okay, so 8 faces.
8 faces.
12 edges.
12 edges.
And 6 vertices.
And 6 vertices. All right. And Derek, did you get that one?
I've got 12 sided,
12 faces.
and then I think it's maybe 30 edges.
It is 30 edges.
And then vertices would be, I haven't counted them yet.
So I'll give you a hint. There's 5 on top, 5 on the bottom, and 10 around the middle.
20.
That's 20. That's right. Okay, so here we go. You know what? Let me just organize this real quick. Let's see if I can data sort, and we'll just sort by this first column. Oh, hopefully. Nope, that didn't work. I gotta here. So data sort by faces. There we go. Now, the question is this: what patterns do we see?
They're in like even increments.
They're in even increments. They're all even numbers. Very good. What else?
Almost feel like some of them are like fractions of each other, or like 4 faces for 6 edges, like that's 2/3.
Okay, we got a 2/3. 4 to 6 is 2/3. 6 to 12 would be a half. 8 to 12 would be, oh lordy, oh, 2/3 again.
Oh yeah.
Kaylee, you see any patterns?
Like for the edges, it goes like 6, and then it goes 12 2 times and 32 times.
Oh, we might be able to cluster them up. Let me do some fancy shading here or this. So we've got this and this. So here, I'll shade it instead. There we go. So the middle two are 12 and the last two are 30s. Is there any other similarity you see perhaps between the middle two that are 12 and the last two are their 30s?
8 and 6 is it?
Ah, the 8 and the 6s are flipped. That's right. Interesting. What's going on here? So first this actually is not quite the pattern we're looking for yet, but I'll take a minute to talk about this pattern. Let me go to the limits of my technical knowledge here and see if we can talk a little bit about why did the 8 and there we go. All right. Why did there we go, 8 and the 6 flip and so on. So let's say we have a 6-sided die like this. All right, and let me see if I can draw this, an 8-sided die. I am not an art person. Oh, maybe I should have Kaylee draw. Kaylee, could you draw these better?
Oh.
No, don't worry about it. I'm just joking. All right, let's take the 6-sided and let's put a dot in the middle of each face. All right, so there's a dot in the middle of each face. And if we connected those dots, the middle of the 4 side faces would make this shape, and they would all connect to the top dot, and they would all connect to the bottom dot. And lo and behold, the faces on the 6-sided die correspond to the edges on the 8-sided die, or the vertices on the 8-sided die. And similarly, on the 8-sided die, if we were to put a dot in the middle of each face, notice there's 4 faces on top, 4 faces on the bottom, and connected them. That would get us a square on top and a square on bottom. And voila, we've got the 6-sided die inside of there. Wow. And I am not going to draw it. Here, let me stop sharing this, close the whiteboard. And I'm not going to draw it, but actually you could do the same thing with the 20-sided die and the 12-sided die. If you put a dot in the middle of each of the faces on the 12-sided die and connected them, you would get this. And if you put a dot on the middle of each face and connected them, you would get that. That's called duality. As cool as that is, believe it or not, that's not the point of this. Let's see if we see any other patterns. Patterns on the numbers. I'll give you a hint. Try adding the faces and vertices on each die and comparing them to the edges. What do we get? So let's take a look at the first line. What's the sum of the faces and vertices? What do you got? 8. And the edges are 6, right? Let's take the second die. So this right here, this die right here. The sum of the faces and vertices. 14. And the edges are 12. What's the sum of the faces and vertices on this die right here? 14, and the edges are 12. What's the sum on the faces and vertices of these die? 32, and the edges are 30. What about the last die? 32, and the edges are 30. You see any relation between those sums and the edges? What's the relation? Yeah, go ahead. You can say it.
Okay, it's 2 more than the edge.
The edges are 2 more, actually. Oh, yeah, it's 2 more. You're right. It's 2 more than the edges. So if we did this, if we took our faces and added the vertices and subtracted the edges, we get 2. And if we copy that formula for all the die, we get 2 all the way down. On all of these die, no matter what, we get 2 all the way down. And any die you have, we will get 2 all the way down like that. Wow.
Yeah, that's cool.
There we go. Now we're really getting into some patterns here. Okay, let's go back. Can you see me now? All right, now you can see me. Well, is that true for any, blocky thing made out of faces? Hold on a second here. Let me get something. All right, I have here a cereal box, Rice Krispies, with a hole in it. All right. Now, let's do our counting on here. So first of all, faces, you might not be able to see, but there's like lines so that each of these little tetrahedron here are a single face. So this is really 4 faces. But let's do the count on this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then on my side, 13, 14, 15, 16 faces. So let's go back to our Excel sheet and put in for this Rice Krispie box, we have 16 faces. All right, now edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we got the inside. Actually, the inside is just like the outside, so that's going to get us 12 more. So 24, 25, 26, 27, 28, 29, 30, 31, 32. It's a lot of edges. So that gets us, I keep forgetting to hit the share button, 32 edges. And last, vertices. It actually isn't that bad. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 on the inside gets us 16 here. And if we continue our formula down, we don't get 2, we get 0. So faces minus edges plus vertices on this thing gets us 0. Now here's the question. Why did all of these, no matter how many faces they had, get us 2, and this thing get us 0? What do you think's the difference?
There's a hole in that one.
Oh, there's a hole in that one. That is correct. The number we have discovered is called the Euler characteristic. If we take any blocky thing made up of the faces and edges and vertices, and we do faces minus edges plus vertices, we're going to get the following formula: 2 minus 2 times the number of holes. So if we have no hole, we'll get 2 minus 0. So 2, that's the number we got, 2. If we have 1 hole, we will get 2 minus 2 times 1, which is 0. If we had 2 holes, if I punched out another hole here, we would get faces minus edges plus vertices would get us a -2. And every additional hole will get us an additional -2. Wow. Amazing. So there's an amazing, miraculous pattern in shapes that just holes. Any questions?
So say you took lots of different holes out of it. You would ultimately get a big negative number.
Yep, more holes we put in here, bigger negative number we get. Always even, so your 2's, remember you observed the 2's were correct. Yeah. All right, so we move on to our next pattern. All right, this is what the top's been named after. What we can learn about things by pouring syrup on them. Now, we're going to take certain shapes, like this banana, this orange, a bagel, still in the bag. I'll take it out of the bag when it's time. Pretzels. We're going to pour syrup on them and see what happens. Now, before we start pouring syrup on them, what I'm going to draw your attention, I want to talk about something. When we pour syrup on things, there are going to be special points. There's going to be 3 kinds of special points on the syrup flow, and those are called singular points. So let me talk about that first, sort of prepare us as what to look for when we're looking at the syrup flow. Okay, holy cow. All right, so the 3 points are this. I'm going to do first. The first 2 is a point where there's a source. A source is where the syrup is going to hit, like imagine it flowing on the orange and all the syrup flows away. So that's a special point. The next is the sink. Imagine the bottom of the orange, which we will not have to imagine in a few minutes because it will have syrup pouring all over it. And all the syrup flows to the point on the bottom of the orange, and that's a sink. Now there's one more kind of point we could have. And think about it. Hold on, I should do this. Think about the banana. Take the banana. And that's going to be a point right here on the underside of the banana. From one direction, front and back, the syrup's going to be pouring towards this point. And the other direction, to the left or right, it's going to be flowing away from that point. All right. So let's take a look at that. And that's going to, come on, whiteboard. There we go. And that's going to look like this. From one direction, the syrup will be flowing towards the point, and the other direction, it'll be flowing away from the point. And then like in between here is sort of flowing that way, right? Okay. Now, what we're going to do is in each of these singular points, identify what's called an index. And how do we identify an index? Well, let's draw a circle around the point, and we're going to start here at each of these. And maybe, you know what would be better? Just thought of this. I should have practiced this ahead of time. I'm going to do a different color. I'm not used to having different colors. We have not yet adopted whiteboard technology here at Loris. We're still on the old chalkboards. All right. Now, what we're going to do is this. We're going to make a little compass, and the compass is going to tell us which direction the arrows are pointing when we're here. And we're going to proceed around the circle in a counterclockwise direction. So for example, next we're going to go here, and now our little compass arrow is pointing this way. And next we're going to go here, and our compass arrow is pointing this way. And next we're going to go here to here, and our compass arrow is pointing this way. And what happens is as our circle goes around, as our little point goes around the circle, our compass is going to make one complete counterclockwise rotation. So that's going to have an index of +1. Okay, so far so good. All right, let's take a look at the next one. At the start, let's take a look at our compass. Our arrow is pointing this way at the start. And as we move up here, it goes down here. As we move to the 12 o'clock position, it's going straight down and so on. As we move here, it goes here. And now this compass, the arrow is going to rotate around. And it's starting at a different point, but it's still one rotation in a clockwise, counterclockwise direction. So that's also a singularity of +1. Okay. Now, last but not least, this is a tricky one. So for this one, our arrow starts pointing this way. What happens when we move up here? Which direction is our arrow going to, if this is a clock, what number is our arrow going to point at when it's up here?
2.
No, 2 is like in that direction. And that's not the direction our arrows are pointing. Like what number on the clock? You can look at clocks. It's not part of the test.
Like a 4 or 5.
Like a 4 or 5. And then as we go up here, it's pointing down towards a 6. As we go over here, it's pointing this way. As we go over here, it's pointing that way. And we're going to make a complete rotation, but this time the rotation is going to go in a clockwise direction. And we're going to call that an index of -1. All right. Got it? Any questions? All right. Now we're all prepped to pour syrup on things. Thing you've all come for. Now I've got to, hold on. I got to put on the camera here because I'm not going to enjoy looking at my pretty face here all the time. You need to actually look at the syrupy things. So I got that in. There we go. All right. So my assistant, Kaylee, you come right here. And I'm going to see and get this like that. Okay, maybe up a little bit. Now we're going to take, you got your gloves on. Good, good, good. And instead of just holding the orange, we're going to skewer it and pale it. Do everything we can to keep you as clean as possible. Here, actually, you need to hold it like that. All right. And we want to, there we go. So there's our orange. Pour syrup on it. All right. Yeah, come on up there. So there we go. So there's our syrup pouring. And well, there's a lot of, okay, so here's the problem. There's a lot of little things coming off, but that's because the syrup did not reach the entire orange. We got to smoosh it around a bit. Make sure the syrup completely coats the orange. To be able to really get the flow going here. All right, can you hold that again? All right, let's try that again. Now the syrup's smooshing orange, got the flow on it. Whoa. All right, how's that look? Okay. Where are our singular points on the flow?
At the bottom.
At the bottom, and where else?
At the top. and
At the
front.
top when the syrup's getting poured on it. That's right. So what's the index of that singular point on the bottom? Everything's flowing towards it. Do you remember what that was? Should we get our pictures back there again?
+1.
It was +1. And what about at the top?
+1.
+1. So what's the total singular points on it?
+2.
+2. Good. All right. So Kaylee, drop the orange into the bag here.
With
All
the
right.
skewer.
Yeah, with the skewer. We got plenty of skewers. They're cheap. Oh, all right. Okay. Next. Banana. Now, the difficult part here is see if you can get like is it syrup all over the banana. Because in order for this to work, we really need the syrup to flow all over the banana. So like put the banana in the syrup down here. What are you doing?
Like, do we do it down like this or up like this?
No. Just right now, we're not even there yet. Right now, we're trying to get it all syrupy. There you go. And flip it around and try to get the other part. There you go. All righty. Okay. Now let's pour the syrup on it. Shall I? Hold on. I'll move the camera up a bit. Oh. There we go. There's our banana. A little bit over. Okay. Let's get the syrup going on this thing. All right. We're going to get the syrup all over it. Okay. Now, despite all those dripping off parts, there's really several places. So where is the first singular point when the syrup was pouring on it?
On the top.
On the top. And what was the index of that?
+1.
1. Where's another point? On the end there. What was the index of that?
+1.
+1. Where's another point?
The other one.
Yeah, what's the index of that?
+1.
+1. And there's one more singular point. I used the banana to illustrate it, in fact. Right in the middle there. What was the index of that?
+1.
Negative.
-1. So 1 + 1 + 1 - 1. What's that get us?
2.
2 again. Holy cow. Is it always going to be 2? All right, go ahead. Throw the banana in here. Okay, good. Oh no, the skewers are skewering the bag. We're getting syrup all over. It's a mess.
The bag is wounded.
Yeah, oh no. Don't tell the custodians. I gotta go take down my posters that implicates me in the syrup mess in Hennessy 350. All right. Well, let's see if it's always +2. What are we gonna do next? We're gonna do a bagel. Maybe you see where I'm headed with this. All right. So first, here, get the bagel all syrupy. This is a little tough because that bagel's hole in the middle is kind of closed up. I guess we're going to have to use our imagination a bit. Imagine that hole is a little wider. All right. Now hold the bagel up. Oh, you still getting it? Okay.
Yeah, just the
thanks.
sides, like I'll do it like this.
Yeah, don't worry about it. I'll give you, oh, good choice. And because you got the gloves on. Yeah, there you go. Gloves keep it all, getting all messy.
Yeah.
Good job. All right, now hold it up by the skewer ends. And I'd like to hold it like this. Oh, all right, pour it over. Oh, God.
Oh.
All right.
Yeah.
So where's one singular point?
At the top.
At the
of
top. What's its index?
+1.
+1. Where's another one?
In the bottom.
In the bottom. What's its index?
+1.
+1. Where's another one?
The side.
No, sides is just flowing past. I mean, if the skewer wasn't there, it's just flowing past the
The
sides.
flat faces, like the middle.
In the middle,
Yeah.
what about the middle, the top of the middle? It's like the underside of the banana, right?
Yeah, it's going there.
So it's -1.
Yep.
And what about the bottom of the middle? It's like the banana on a smiley face up.
Yeah, the other side.
Right, and that's gonna be -1 too.
Yep.
So 1 + 1 -1 -1, what's that gonna be?
0.
0. Oh, it's different. Why do you think it's different?
Got a hole in it.
Because it's got a hole in it. Holy cow. This was just like that previous thing. All right, hold on a second here. Let's see how well you're hiding the evidence. Here, Kaylee, drop that in here. Okay. I did not count on the fact that the skewers would rip open our garbage bags and make a mess of everything everywhere. Now, this is a tricky part. And you know what? Kayla, why don't you take off your gloves and throw them away? We're going to stop the actual syrup part of this. We're going to go, stop sharing, because see, my problem is I usually get a big pretzel for the next one. And all I could get were these little ones. That's all I could find. All right. So we're going to have to do this mentally, not actually with syrup on it. So let's take this pretzel and imagine we're pouring syrup on the top of it right here. Like right here. Okay. What do we got? We got a +1 singular point here, +1 singular point there. It's 2. And then in each of these holes in the top and bottom are -1, -1, -1, -1, -1, -1. Okay. So this is going to be a -4. Okay. So what do you think the sum of the index points on these things will be? Well, it's going to be 2 -2 for every hole we have, because the top of the hole is a -1, the bottom of the hole is -1. So it's 2 - 2 times the number of holes. Where have we seen that formula before? The Euler characteristic. The Rice Krispie box. So the sum of the singular points are the Euler characteristic. That is, I wrote that down here somewhere. Okay, that's called the Poincaré-Hopf theorem. So they proved that if you have a vector flow on a surface, you can find all the singular points, no matter how it flows on the surface. You count the singular points up, the indices, and you always get 2 - 2 times the number of holes, no matter what shape it is. That's why the banana and the orange had the same number, because they're really just the same thing. They have the same number of holes, no holes. Okay. Any questions or comments on that? All right. One last part. Kayla, you can sit down if you want. Thank you very much for all your help. But this last part is just sort of watching it. We'll draw pictures here. All righty. Get a whiteboard back up again. Okay. Now, and let's get drawing. In mathematics, we sometimes are looking at something called curvature. Curvature is how curvy curve is. So let's say we take a parabola here. Oh, I'm still on red. Yeah, red's fine. We'll keep it red. So what's the curvier point, A or B? B is the curvier point. Now, how can we actually measure curviness of a point? Mathematicians have a way to do it. Now, I'm not going to tell you how mathematicians actually define it, but I'll tell you what it's equal to. Way to see it. Imagine you're driving a car along this road and you're right here and it's turning a bit. It doesn't look like it's turning, but it is turning a bit. And you decide to lock your steering wheel in that position. Now you're going to leave the road. What path will your car take if you've locked the steering wheel in that position?
It'll veer off.
It'll veer off, and then where will it go? Go towards the middle. Where will it go from there? We've locked the steering wheel in its position.
Oh, it'll ultimately make like a circle.
It'll ultimately make like a big circle. Okay. Now let's say we're down here and we lock the steering wheel in the position. Where will the car go then? It'll go towards the middle. What shape will it go in? A circle. Will that circle be bigger or smaller? than the smaller. So the more curvy the road, the smaller that circle will make. Okay, so mathematicians have a notion called Gaussian curvature, which we use K by, and a way, and this is actually a way, this is not how we calculate it, but a way to get it is we take these circles, and then if this is the radius of the circle, we do 1 over the radius of these circles, because we need to make it, the smaller the circle, the bigger the curvature. So this is a big circle, we'll call this like capital R here. All right, and so the curvature here is 1 over capital R, and the curvature down here is 1 over little r. And this will be a smaller curvature because it's got a bigger r, and this will be a bigger curvature because it has a smaller r. Okay, does that make sense?
Yep.
All right, good. Now let's go to surfaces. Like let's just take a surface like this. Okay. Now, how can we define? Well, hopefully you've seen surfaces like this on Calc 3. Think of this as like an upside down cup. Now, how can we define curvature here? Well, 2 things. First of all, if a curve is face up, we say it has positive curvature. And if it's face down, we say it has negative curvature. Okay. And secondly, what we do to find the curvature of the surface at a point is we take the curvature in one direction and the curvature in the other direction, and we multiply it. So for this point right here, we have a negative curvature here because it's going down, and a negative curvature here because it's going up, or a negative curvature here because it's also going down. And we multiply them and we get a positive number. And that is what's called the Gaussian curvature of the surface at this point. All right. So let's take a look at if we have a football shape here. Okay, at the top here, we're going to have pretty extreme curvature in both directions, positive curvature here. If we go to the side here, the curvature is a little less. The curvature here is actually not that much. The curvature here might be impressive, but it's not much here. So when we multiply them, we'll get less curvature. As you can see, we'll get the biggest curvature at the tips of the football. And actually around the side here, we would get the least curvature. So does that make intuitive sense? All right. Now, here is another pattern. I need a new sheet. How do I get a new sheet on this? Is it this button? There we go. All right. How do I get rid of this? I go back here. Okay. Now, let's say we take a shape like a sphere. Okay. And we freeze it. And we take a hammer and we shatter it into tons and tons of little pieces. Okay. And we get each little piece here like this. Each little piece is going to have a curvature on it. Okay. And let's multiply the curvature of that piece times its area. K times area. And then we take all of these little pieces, K times area, and add them together. All right. On this sphere, that integral will, or that area, I use the word integral. As our pieces get smaller and smaller, if we take the limit as our piece size, we'll call it delta P for piece size. As our pieces get smaller and smaller, that actually goes to a limit, an integral. The integral of the Gaussian curvature on our surface, according to area. And that on any size sphere is going to be 2 pi. Now, you could say, take a big sphere and say, well, the curvature is not that great. It's pretty flat, but there's a lot of it when we multiply by the area. As the sphere gets smaller, it's really curvy, but it's got little area, and it all balances out, and they all will get us 2 pi, no matter the size. If we squash our sphere down and make it shaped like this, and we freeze it and we shatter it into little pieces and add them up, multiply the curvature by the area of each little piece and add them all up, we will also still get 2 pi. But if we take a donut shape and freeze it and shatter it into a million little pieces, and for each piece, multiply the curvature of that piece times its little bit of area, and we add them all up, that'll get us 0.
That's crazy.
Yeah. So 2 pi for the sphere, and any shape we can squash the sphere into. 0 for the donut. Does anyone want to take a guess if we take a figure 8 shape? Freeze it, shatter it, multiply the curvature by the area, add them all together. What do you think we'll get there? Negative 2 pi. What if we take our pretzel with 3 holes in it, shatter it? What do we get? Negative 4 pi. That's right. If we take our curvature at each piece, multiply it by the area, and add them all up, we're going to get 2 pi times the Euler characteristic. So each of these are really interesting patterns in their own right, but also they're all the patterns of the same thing themselves. So first, what we got, our first result was our, given all the dice or the Rice Krispie box, our faces minus edges plus vertices will always give us 2 minus 2 times the number of holes. We use G for genus. Genus is the mathematical word for holes. Then when we poured syrup on things, we took the sum of the indices of the singular points over the singular points. So we just added up the finite number of singular points, and we got the same thing. And lastly, third, oh, and I said this one is called the Gauss-Bonnet theorem. The Gauss-Bonnet theorem, this was the Poincaré. Oh, come on, I'm having such a hard time drawing. Why isn't this drawing? Poincaré-Hopf. And then the integral of the Gaussian curvature, according to area, no matter what the shape is going to be 2 pi times 2 minus 2 times the genus. And this is called Gauss-Bonnet. Oh, come on. N-N-E-T, there you go. And this one here is discovered by Euler, so it's the Euler characteristic. So this is not only patterns, but patterns among patterns. All right. Any questions or comments from in person or online?
I thought it was interesting how you related all the die to the objects to the 3 formulas.
The die to the like syrup, yeah, to the curvature thing. Yeah. Yeah, that's then math is a science of patterns. And so it's obviously mathematicians who first saw these patterns on all the different dice, no matter how many faces it had, and then expanded it to shapes that have holes in them, then found out the same thing for syrup on surfaces, and then realized it was the same formula between the two, and then found a similar formula for the curvature, and then found it was the same formula. So we got patterns on patterns on patterns on patterns. Math as the science of patterns. All right. Well, thank you very much for coming. I appreciate the company, and enjoy, and have a good day.